Hello again, glad to be back, and I'd like to talk to you this time about free body diagrams. Now this is a real basic topic, it's really important. If you're going to do statics or strength of materials, you're going to be doing free body diagrams. They sound a little abstract at first, but once you get the hang of it, you're going to find out it's pretty easy, and it's going to become fairly intuitive. Now I'm going to start off with an example that seems kind of silly, but trust me, it works. Now when I was a little kid, I used to like to watch cartoons on Saturday, and every once in a while they'd have something in a Bugs Bunny or something cartoon that you just knew wouldn't work. And instinctively you knew it wouldn't work, but you couldn't quite figure out why. Well, free body diagrams will give you an example. Now here's one of the examples that I saw. Now this is a little silly, just bear with me here. Let's say you've got a boat, okay, sailboat maybe. That's a sailboat. And there's no wind, okay? So, but you've got a sail here. Here's the mast. Well, that's some mast. Here, let's make that a little smaller. Wavy mast. There you go. And there's a sail here, all right? There's my sail. Well, the sail needs wind to make the boat go. And so what the Wile E. Coyote or Bugs Bunny would do is they'd put a fan on it, blowing air into the sail, and the boat would go. Now, you look at that and you go, now that can't work. But why can't that work? Well, free body diagram makes it clear why this can't work. So what I'm going to do here is let's get rid of the water for right now. I'm interested in forces that go this direction, okay? And the water makes a buoyancy force that goes up. So there's the bottom of the boat. Now we've got this object here, okay? And all a free body diagram does is it separates an object from its environment, okay? That's the free body part. Here's the body is my sailboat with this little fan on it, and it's free. It's now been freed from its environment, so it's just kind of floating in space. In fact, if I wanted to really draw a circle around it, I'm going to erase the circle in a second. It's kind of in the way, but see, there's the body, and I've separated from any forces around it or any connection with anything else around it. So that's the free part, okay? Now, what I want to do is I want to show the forces acting on the body from the outside. Well, there's vertical forces from the water. I'm going to ignore those for right now just because the vertical forces keep the thing floating, but they don't move it back and forth at all. And so what I want to do is, from my body here, what forces are coming in from the outside that would make this boat move forward or move any direction? Well, there aren't any. The fan is stuck to the hull. The mast is stuck to the hull. So this hull feels the forces, but the boat as a whole has no net force on it, so it's not going anywhere. Okay? So let's do something here. I'm going to put what's called a fictitious, well, that actually worked pretty well, a fictitious cut, all right? It's not really there. Okay? It's not really there, but we're going to imagine there that we've cut the hull of the boat in two right there to look at what forces are acting. Well, the boat's, the hull, or the sail's pulling that way, and so there's now going to be a tensile force on the hull right there, so there's going to be a force that way coming across that part of the cut, and this is making a force that way, so there's a reaction force that way, so this is pulling. Excuse me, I think I've actually got those backwards. Let me get this correct. Okay, those are pulling against one another, okay? So that part of the hull is in tension right there. That's what that fictitious cut tells you, okay? So this is what a free body diagram does. And I'm going to give you a little more relevant one here in a second. While I'm erasing this, I'm going to give you homework. First time ever in these videos, I'm going to give you homework. Go Google, I don't know, Bugs Bunny, Wacko, Yakko, and Dot, whatever your favorite cartoon is, and you'll find a scene in a cartoon somewhere where a character, Bugs or Wacko or somebody, hops into a basket, reaches out, grabs the handle, and lifts himself up. We know that can't happen. Why can't that happen? Well, draw a free body diagram. You'll find out there's no forces coming in from the outside there's no net force on that basket. The basket itself feels the forces, tensile forces between maybe the bottom of the basket and the handles, but if you draw a circle around the character in the basket, you're going to find out there aren't any forces coming in from the outside that would lift that basket off the ground. So see, free body diagrams lets you understand Bugs Bunny. You heard it here first. Let's go to a more perhaps serious example, and what I'm going to do here is I've got a little 3-bar truss I made up, okay? And I'm going to explain this in case you haven't seen this kind of thing before. and I'm going to show you how to do free body diagrams on this. All right, I'm going to keep this short. So here's a truss, and it's pin jointed truss. It's bars made out of some metal probably, and they're joined by pins at the corners. So there's no rigidity at the corners. The corners can rotate if they need to. Okay, I've got it pinned to something that isn't going to move. This part of the diagram right here with the hash marks indicates that there's something big and immovable over there. So imagine that's a giant concrete wall. Same thing down here. Let's imagine this is, again, something that's big and not going to move. All right? So that's another wall maybe, or floor. And those little rollers right there indicate that there can be force in the vertical direction, but no forces in the horizontal direction. It's free to move that way. Okay? So this is kind of a shorthand. It's almost a visual language we use to communicate information in a very compact way. All right? So I'm going to get rid of all this extra stuff here because it's going to get in the way. But when you see that kind of stuff in a free body diagram, that's what that means. Okay? So let's say I want to find the forces there and there. There's going to be reaction forces. I can transmit force in the vertical direction at this point and in the vertical and horizontal at this point. Well, the first thing you're going to need is a coordinate system. So always, always, always draw your coordinate system. Okay? So I'm going to put X and Y. Those are the positive directions for X and Y, and if there's moments, okay, put that on there too, okay? Most of the time I'll use this one. Unless I have a pretty good reason to do something else, I'll use this one. Right now, this is the one we're going to use. So how do I start drawing forces on this? Well, let's cut the body away from its supporting structure, okay? Make it a free body. It's now just sort of floating in space. Well, the problem is there's one force that isn't opposed by anything else. If this really was the only force on it, it would be accelerating and rotating and everything else. The whole idea of statics is, and strength of materials usually, is that the body is in static equilibrium. It's not accelerating. All right, so there must be opposing forces. All the forces have to add up to zero. So I know there's a force there, and let's see, I know there could be a force that direction, and there could be a force that direction. Now you're going to see right away, this is going to turn into as much of a bookkeeping exercise as anything else. So I'm going to give numbers to these different grid points, okay, or these different connection points. I'll call that 1, 2, and 3, okay? So actually, let me do this the other way. I want to go from left to right here. Let's call it 1, 2, and 3, okay? And a circle around it indicates it's a point. All right, so I'll call that F1x, F1y, F2y. There is no F2x because there was a roller there. Okay, this is a free body diagram now. I've got the body isolated, okay, and I've got all the forces acting on it right now. This is going to be a lot easier to deal with than that original drawing we had, all right? So I'm going to stop here. I'm going to keep working on this problem in the next maybe 1 or 2 videos. We'll talk about this some more, and I'll work some numbers out based on some dimensions and that force. Remember, free body diagram, you separate the body from its environment, draw all the possible forces on it, and now you've got a nice, clean, consistent drawing that you can use to start calculating results. Hope this helps, and I'll see you next time.